Welcome. In this video I'm going to show you how you can obtain hedges in G for one sample scenario using R. I'm using Jupyter Lab, but this should also work in R Studio, for example. This video will focus on how to obtain hedges G, not so much if you should. To show you how this can it's actually a correction for Cohen's D and an effect size measure. To show you how this can be done, I need some example data, so I'll load in the general social survey data from 2012, adjusted for some example purposes. I only need one numerical field, so I'm going to be using the age field, remove any of the missing values. There is an 89 or older category in there, so I'm just going to replace that with 90, a quick fix for this example, and then make sure everything is numeric. I also need an hypothesized mean, which I'm going to set to 50. This is really a free choice. It depends on your research, what it is you want to use. I have a separate video where I show you how this can simply be done with my own library that simply has a function for this. But if you don't want to use my library, you can also use the f-size library. It has functions for Cohen's D as well. If you need to install it first, then you can load the library and then use the field, the hypothesized mean, and that you want a hedges correction. And there we go. It's a minus 0.01. It even gives a rule of thumb that it's negligible. I think that's about it. It gives a confidence interval, so that's quite nice. If you don't want to use any libraries, then we first need to decide on or determine how large our sample size actually is. So that's 1969. The degrees of freedom would be the sample size minus 1. That might be useful later on. The sample mean, so that's the mean we actually found in the sample, is simply add everything up and divide by the number of items, but R has simply a mean function for that, and as you can see, that will give the same result as that one. So if I run this, you see indeed the same result. We need the standard deviation, which is this complicated formula. So we take each score, subtract the average, and square that result. Then sum all of those up, divided by that degrees of freedom, and take the square root. Again, R has us covered with its stats library, and it has their SD, which can calculate that for us. If you want to use the formula, it's like this, and these two should give us the same result. Cohen's D itself, which is actually also hedges G, uncorrected, which is simply the the sample mean minus the hypothesized mean divided by that standard deviation. So in this case, that gives us minus 0.106. Now hedges G actually adjust this by using this formula. So that's an approximation. And we have all we need is just a bunch of numbers, so you can just fill out the formula, and in this case that comes out to be minus 0.15. Slightly lower, or actually higher than the previous one. It does also provide an exact formula, which is using the so-called gamma function, which, as you can see, is over here, is this complicated one. The m itself, actually, that we need in there is just the degrees of freedom divided by 2. And that gamma is actually also luckily available in R, so we can simply use this one. It returns not a number because it's too high. We're trying to calculate the gamma of 984, and that's simply too much for R to deal with. So either we should do all the math ourselves or just use an approximation. If your m isn't too large, I think as long as it's 171, it should be good to go. 172 becomes a problem. In my case, I need to use one of those approximations. There are other ones who actually also suggest approximations. For example, Hedges and Olkin, they come up with this one. We have everything here again that we need for that, or Durlock, who shows another factor like this one. So yeah, you can use different ones. So let's see how this one actually would look like. Square root is the same as raising something to the power of a half. And you can see it's very similar. Xu also gave this long formula. It looks complicated. It's the 12th root, so that's why I'm doing here to the power of 1 over 12. But everything else is actually just filling out that formula. And that gives the same or similar result at least. Alright, I hope this video was helpful, and thank you for watching.